Have you ever heard the term Ohm's law? This just means that if you're relying on your meter's resistance reading in your diagnosis, you could be missing out on some very important information. In fact, when some electrical circuits are energized with AC voltage, they can behave quite differently than your resistance readings might imply. This is because some components, like inductors, react in a certain way to AC current. This video will demonstrate this phenomenon by going through a refrigerator inlet valve exercise, briefly showing how inductors actually work from a theoretical standpoint, describing how the current draw of motors and transformers is many multiples less than your ohm readings may imply, and how they are in effect variable inductors. You'll also see how solenoid cores are a key component of their function, and how unsuccessful insertion of their cores can have profound implications in how they can fail. So this refrigerator inlet valve is an inductor. If you were to measure the resistance of this coil with an ohm meter, you would be passing DC current through it, which doesn't take into account the coil's inductance. The DC resistance that the ohm meter sees in this case is 188 ohms. So that would tell you that if you had 120 volts DC across that coil using Ohm's law, you would have 120 volts divided by 188 ohms, or 0.64 amps of DC current. Just to confirm that a 120 volt DC source would see 0.64 amps, we'll connect a DC power supply to this solenoid. However, for safety reasons, we will only connect a multiple of that, which is 12 volts DC. That's okay though, because based on Ohm's law, voltage, resistance, and current are proportional to each other. Thus, if we connect only 12 volts DC to this coil, based on the proportionality of Ohm's law, we should get about 0.064 amps instead of 0.64 amps. I have this power supply set up to 12 volts, and you can see on the display that we are getting 0.063 amps, which is pretty much right on the money with our calculation. However, to AC current, the ohms, if you will, that the coil presents is much higher because of the inductance of the coil. Actually, it's inductive reactance to be more exact. All coils have inductive reactance. The impedance of the coil is a combination of that inductive reactance and the resistance of its wire. So if we hook an AC voltage source to this solenoid, you would see much less than the 0.64 amps of current draw. So I'm going to go ahead and plug this in and get a reading. We have 0.44 amps instead of 0.64 amps that we would have with DC voltage. So what does that tell us? Well, we can easily calculate the impedance presented by the coil now by using the Ohm's law triangle and replacing resistance with impedance, which is voltage divided by current, or 120 volts divided by 0.44 amps, or 273 ohms. So instead of 188 ohms, we have 273 ohms, which is a 45% increase in the ohms that the AC supply is seeing. The impedance of this coil, by the way, is a combination of its measured resistance and its inductive reactance. Here's a little bit more about how that works. Inductors, by their nature, resist changes in current. They do so because if you try to change their current, you are changing their magnetic field. When this happens, they react by inducing a voltage across them, called counter EMF, in a direction that imposes that change in current. The result is an overall opposition to AC current flow. This opposition is measured in ohms and is known as inductive reactance, or XL. It combines with the coil's measured resistance to comprise an overall impedance. Here is the simplified equivalent circuit of an inductor. It is an ideal inductor in series with a resistor. In our case, the solenoid's inductive reactance, which I calculated earlier, is 198 ohms. We know that the resistive component is 188 ohms because we measured it. Now you just can't add these together. The overall impedance, or AC resistance of the coil, if you will, is what's known as a vector or Pythagorean quantity. It is the same way that you find the hypotenuse of a triangle. So with a little bit of trigonometry, we have r squared plus xl squared is equal to z squared. If we take the square root of that, we get an impedance of 273 ohms, which is what we measured in the demonstration. So as you can see, the measured resistance of the coil, or measured resistance of any inductive load like a motor, is going to be much lower than the AC voltage source sees, due to the additional opposition to current flow from its inductive reactance. In larger inductors such as motors, this effect is much more pronounced. In fact, the impedance of motors, when running at their specified RPM, can be many multiples of their measured DC resistance. By the way, the impedance of induction motors, which from an electrical standpoint are essentially transformers, decreases as you increase the mechanical load, which is why their current increases under load. If you were to lock the armature on an induction motor, the current through the armature cancels out much of the stator's counter EMF, making it look much less like an inductor and drastically increasing its current. Transformers work much in the same way when you draw more current from or short out their secondary winding. Another thing that is good to know is that the impedance of solenoids greatly increases when the plunger or the core inserts itself into the coil. If it doesn't, the impedance is too low and the current is too high, resulting in an exponentially greater amount of heat that the resistive portion of the solenoid has to dissipate and is often responsible for melted solenoids that you may encounter. It is also common with HVAC contactors. So that's just some extra inductor-related info that might come in handy someday. In closing, don't let static ohms readings bite you in your diagnosis. Consider the fact that some components, when subjected to AC current, like solenoids and induction motors, will draw much less current than your meter's ohm reading would lead you to believe. So that's it for this video. I hope it has been interesting and informative. If so, please give it a thumbs up and subscribe to this channel.